Hey there, in this video we are looking at Appendix B to the Carrano Walls and Mirrors in C++ text. And this appendix presents some important themes in programming. Now, there's also an Appendix A that gives a review of the basic syntax of the C++ language that you can review as you start your data structures course. But I want to spend some time on this appendix that covers more how you're going to use the C++ language in an intelligent way, or really any programming language. It's common to any kind of software engineering really here. And I think this is important because it covers some bigger concepts that new programmers frequently struggle with. Hopefully this is mostly a review. Hopefully this is basically the same thing as we've emphasized in our prior programming courses. And the point that I want to make here is that sometimes students in my programming courses take away a misperception, something like Mr. Collins has some weird, oddball opinions about how you organize and style your code. But the truth is that for anyone that's worked in software engineering, these are just facts. These are truths that we all agree need to be done to maintain a code base so that it's readable and usable for a large number of people over a long period of time. So you should check that out. Read Appendix B on your own. Confirm whether it's the same thing that I have said, whether it's the same thing that your prior textbook in C++ said. We basically all agree that you need to keep these things in mind in order to have a reasonably usable, maintainable code base. So let's start the review. First of all, modularity, that's a term we've used before. Modularity is separating code into small components, and we probably used that word the very first time when we were presenting the idea of functions in a programming language like C++. And modularity, keeping these sections small and short, helps to reduce complexity and gives you a whole lot of other benefits, including it makes it easier to construct the program. If you can write one little function, like maybe 7 lines long, and test it one little chunk at a time, rather than trying to tackle a 1,000-line program all at once. It makes it easier to debug the program because it's easier to find the section where the problem is. It's easier for other people to read the program, that they can read it in small little chunks. Same reason that you break up your writing into paragraphs and sections in a piece of writing. It's easier to modify the program because, again, you can find the one section you need to change to add a feature or change a feature. And it helps you eliminate redundant code, which I normally refer to as the don't repeat yourself principle. If there is some kind of feature or function that happens a number of times, isolate it into one module and maybe into one function and just call it every time you need to, and don't keep rewriting it and keep maintaining it in different places. Lots of advantages, and that's a theme that we'll hit on again in a number of ways here. Okay, styling your code. Again, something that I emphasize in my prior courses, something that the Carrano text here says pretty much exactly the same thing. First of all, don't use global data. Do not use global variables. C++ is an older language, and it does allow that. The compiler will know what that is, but nobody does that anymore. It's just too dangerous. If you have a global variable and somehow it gets corrupted, where did the corruption happen? Where do you need to debug it? Well, the problem is it could be anywhere. And if you have a 100,000-line program, you have a real problem finding the place that corrupted the global variable. So don't do that. Do use private data members in your classes. And that's something we did all the time in our second semester of C++ programming, is that our class data was always made private so that it could only be accessed directly from within the class itself. If you need to provide access to that data externally, then use accessor and mutator member functions appropriately. Not every data member is going to have an accessor or mutator, just the ones that are needed externally. So notice that both of those first two bullet points are about reducing the scope of a variable. Ideally, you want to make a variable in your code accessible in the very minimal, smallest place that you can get away with, because then that's less for other programmers, for you or other programmers to have to remember, less mental space that they need to remember that variable if the scope is reduced as small as possible. Third bullet point here, use reference parameters appropriately. Remember that the normal thing when you're passing parameters into a function would be passed by value where there's a copy being made. And again, that's kind of a security thing. If the function changes that variable, the original variable external is not affected in any way and is still completely safe. There are some cases where you need to pass a parameter by reference so that it can be changed, right? If the purpose of the function is to change a piece of data, then it would have to be passed by reference. Or maybe if for some reason you effectively need multiple return variables, multiple return values, you could do that. Also, if you're passing really large structures into a function, passing it by reference avoids the big copy that would spend time on the CPU and spend space and memory that you don't really need. Best thing you can do there, if you don't need to change your big structure, pass it by a constant reference. And hopefully you've practiced that a bunch of times and you will continue to do so. Now, fourth bullet point here is the Carrano text recommends having your method calls only one level deep. And I'll be perfectly honest, it's not something I had actually thought of myself until I read Appendix B. And now I think it's a pretty good idea, actually. So if you have a class that has another aggregated object inside it, okay, you're going to reference that secondary object. And as a programmer, you need to know what that object's member functions are. So you'll be saying object.method1, object.setLength, object.getWidth, something like that. But what you don't want to do is you don't want to have that second object contain a third object and then be calling methods on that. So you don't want to have object1 dot get object2 dot set dimension, something like that, and have that multiple levels deep, because it interconnects those objects too much. It'll make it hard to swap it out later. And now other programmers need to know about all these objects in the entire system when you do that. So if you are aggregating object 1 contains object 2, have object 2 present all the public methods that you need to make sense of that object. So that's kind of an interesting piece of advice that I've started using in my own programming, frankly, lately, since I read that. And then the last bullet point here is make sure you handle errors gracefully and don't have confusing, corrupting things happen when errors occur in your code. We're going to come back to that a number of times during the course and present some other strategies for handling errors like that. Okay, readability. Actually, how does the code get presented? Same stuff that we've said in our prior courses is what's in the Carrano text here. So as far as naming your classes, the names of classes should be noun phrases and they should be singular. Like a good class name is rectangle, not rectangles plural, not get rectangles. It should be a noun phrase like rectangle. Capitalize the first letter, and each subsequent word in your phrase should also be capitalized. We generally call that camel case for identifier names where most of the letters are lowercase, but just the first letter of each word is uppercase. So you kind of see these humps in a phrase like a camel. So camel case, class names, and for classes, the very first letter is also capitalized. Now, function names should be verb phrases. Functions are things that do something, so they should be verb phrases. Again, camel case, in this case, you start with a lowercase letter, and then subsequent words in the phrase are also capitalized. Variable names, exact same as functions, actually. Camel case, you start with a lowercase letter, and later words are capitalized. Now, for named constants, and I'm sure you've seen this before, named constants are entirely uppercase. All the letters are uppercase. And then when you need to separate the words in a multi-word phrase, we use underscores for that. So that's just traditional and standard. Your control blocks, when you get into a control structure like an if or a while or whatever, should get an additional indent, indent space to make that visually connect together, basically. Your indentation should be consistent. And for what it's worth, in our course, every level of indent, we use one tab character. Now, a lot of people in the world prefer to use, I don't know, 4 or 6 or whatever spaces. In our course, we use one tab character, which is the same as the Deb C++ default, for what it's worth on that. And also make sure you have clear documentation. When we say documentation, we're talking about the comments to a function, to a class, maybe inside a function if the function's getting long. And we'll return to this point with some additional ideas about what's called Java doc style comments, a particular way of formatting comments when we look at Appendix I, which will be a follow-up video later on. Modifiability. Now, in your prior courses, you've probably been writing a program once from scratch and you submit it for an assignment and maybe you get a grade. That's the end of it. It's fire and forget. You just write it once and you basically forget about it. But remember, in a professional setting, the code that's getting written is going to have a fairly long lifespan. It's going to get evolved. It's going to get modified. It's going to get maintained, we say, by a number of different programmers over the years as it gets changed, as it evolves, as they add features, as they fix bugs and things like that. So one of the very top challenges in software engineering is keeping the code readable and understandable and reasonably short, even when it's being evolved over maybe generations of programmers. So you kind of want a lot of what we talk about in C++, and a lot of what we talk about in our programming courses are features to try to support that maintainability, that ability to easily make sense of and modify code over many years or decades or generations or something like that. So here's just 2 starter ideas on making it easy to modify code. Number 1, like we said on the last slide, use named constants. If there's a specific important number or maybe a specific important string that pops up in a number of different places, don't repeat yourselves. Don't repeat that magic number. Use a named constant, like maybe New York sales tax rate equals 8.875%. And then use that constant where you need it throughout the code. And what that does is that on the day, at some point in the future, when that tax rate does in fact change, it's easy to modify the code because you just need to change it in one place instead of hunting down, finding a bunch of places that it got used and making sure you don't forget any one of those many places. So use named constants. The other thing that the book recommends, and you'll see a couple of examples at the start of the course here, is use named types. If there's a specific type, like int, float, char, bool, whatever, that you suspect may need to change at some point, what you can do that's pretty smart about that is use a typedef statement. And again, typedef for a definition of a new type basically just gives a different name for an existing type. You can use a typedef to indicate that particular type. Use your new name for the typedef in your code. And then if the type needs to change, again, you can just change it in one place on the line where the typedef was defined, very similar to using a constant. So that's kind of smart. I don't do that a lot myself, but I can see the point of it. So if I have a variable that I think needs to be an integer all the way through, okay, typedef my value as an int. And then if it turns out I really need decimals, like this actually did happen to me recently, and then if later on it turns out that I really need to use decimals, I can just change that typedef to a double in the one place, no problem. One of the things that's going to happen in this course is, again, if your prior courses were kind of fire and forget, you just write your code once and forget about it. This course in data structures, you're going to get a little bit more experience with taking some existing code that maybe we will give you out of the book to begin with, and your job now will be to maintain it, to modify it, to add a feature, things like that. And so part of your task here will be, number 1, reading existing code and making sure that you can understand it, and you'll get some experience about like why is it important to have code that's easy to read in standard style, because that's actually going to be the start of the job. and then you'll go in and maybe you'll add one feature or two features in an intelligent way, hopefully, and you'll get a little bit more experience with this idea of maintaining an existing code base that we were only able to just talk about in our earlier introductory courses. So that's actually something I'm really looking forward to this semester. Okay, ease of use for the user of the programmer. We're not talking about the programmer. We're talking about actually the end user who might possibly use your application. Make sure that your user interface on screen is clear and easy to read. Make sure you're using, standard English. Give clear prompts before an input. Before someone needs to type something in, give a clear prompt about what they need to do. Our book here recommends echoing the input that your program gets on screen so the user can confirm that what they intended to input actually was received properly. And then again, as I normally say, give clear labels for any output. We're never just going to print a number to the screen. That's not intelligible or useful to the end user. So make sure you give a prompt of today's average temperature was this many degrees Fahrenheit. Get the units in there. So always have a clear English language label for any kind of output. Again, that's what Carrano says. I totally agree. It's the same thing as we've said before. Important stuff. The book here this semester, we're going to focus on increasing the safety of our programming, what Carrano calls fail-safe programming. So try to guard against errors in the input data. So as input comes in, you should test for invalid data. And if invalid data is identified, you can either have the user re-input the data, maybe with a while loop, like keep going until they get it right, or have the function return an error code. Maybe what we've done in the past is we've had search functions whereby if the thing you're looking for just isn't in the array, return -1. And that's the special code indicating we didn't find what you're looking for, something like that. We will have some additional strategies that we'll present this semester that we didn't have time for before. And then guarding against errors in the program logic. So if you have a function that's computing some kind of result, hopefully there's ways you can think of to check that the result is reasonable or what you expect. And some things that we might do this semester to that is use what's called an assert statement in your code, which is just assert and then some kind of Boolean value. And the assert statement actually just ends the program if the Boolean comes out false. The other thing you can do a little bit more advanced than that is use what's called an exception, which transmits an error code to another part of the program in some kind of sophisticated way, I guess I'll say. We'll dig into both of those techniques when we get to interlude 3 on these error handling techniques of assertions and exceptions. Me personally, I actually use a whole lot of assertions in my code. So I will be looking forward to when we finally have that in our toolkit. When you're working on larger code bases, you need to frequently interface with exceptions because that is a standard programming tool these days, I would say. Okay, let's say you're in a situation where there's a bug. There's a problem in your code and your programs are getting larger and larger. What are some strategies you can use about how to approach fixing the bug? And hopefully you've done this before. One strategy is to use some temporary cout statements to find where the logic errors are. So you go in at what seems like the danger spots, print out the current state of the variables or the current state of the array to confirm what's currently happening at that point. You can also use the IDE, the Integrated Development Environment's breakpoints and debugger. If you've watched my prior videos, I frequently do that myself in Dev C++. So put a breakpoint, have the program run up until that point, and then it stops, and then you can step through the code one line at a time and keep an eye on what the variables currently are. And sometimes that's a really good mechanism. For larger programs that are doing a whole lot of work, or like maybe there's like a function or a loop that's going to get called, I don't know, thousands of times, it may not be super useful to put a breakpoint in that function when the problem isn't going to happen until that gets called like 5,000 times. So like in a recent project I was working on, I was having to rely on mostly a whole bunch of cout statements for the critical things that I was really looking for. So, they're both in different times useful strategies. Now, things to check with the cout statements that you're putting in temporarily: check the arguments at the start of a function, right? Check in, make sure the arguments make sense or they're within the valid ranges or things like that. You can print out the variable state right before a loop and right after a loop to see whether the behavior of the loop was what you expected with the setup and the finish state. You can print out the value that you're about to test right before an if statement and see whether that if statement is working properly. And then one idea is, if you really get into the weeds and you really get in trouble, you can start writing dedicated dump functions that are just printing a whole bunch of important information on screen. So if you have a class object with some data members, you got length, you got width, you got area, whatever, maybe you've got an array, and you could make a function that prints all that information on screen and then call that function from multiple important key places, and hopefully that'll help you find the place where things went off the rails. Okay, so a dump function, kind of interesting. Not something I do a lot, but maybe I will start. Okay, testing. So again, you're writing some code, and testing is one of the most important things you do in software development. When I worked in the past, we had an entire dedicated department just for testing our code. That'll vary based on the company or the business. So think about how you're developing your test data. And one recommendation here is to test the boundary values. So if you have a function that is to make sure someone's old enough to, get into a music event, maybe they need to be 18 years old or something, I would test to see whether it's right. I test an age above 18. I would test an age below 18 that hopefully gives you the rejection message. And I would definitely test the number 18. And presumably 18 should be okay. But test that number 18 because that's frequently where the most common problems occur, is on the boundary value, right on the cutover from good to bad. If I'm working with integers, I always test the number 0. Frequently there's a problem with the number 0. I test the number 1. I test some positives. I test some negative numbers. Things like that. If I'm working with doubles, I test some whole numbers. I test some numbers that actually have fractional places. There's an example in the book here that I think is good. Let's say you're making a function to do a linear search of an array. I would want to test that a number of times. I want to test it with the target value that I'm looking for being the very first thing in the array. Try it when the thing that I'm looking for is the very last thing in the array. Try it when it's somewhere in the middle. Try passing in, and this is something we probably haven't done in the past, but what happens if you pass in an empty array that's size 0? Does your function still work then? And hopefully for like linear search, it would say, we can't find the thing. And hopefully the program doesn't crash. What happens if you pass an array of size 1? What happens if you pass in a larger array? And ideally you'd test all those things because the common breakdowns would be around size 0 or size 1 or something larger than that. So there's some ideas. And I think we just listed, for that linear search example, we listed at least 6 or 7 or 8 different things to test that we would want to test all of those. One recommendation here is you're writing some additional code. Maybe you've written some cout statements. Maybe you've written these testing statements for the actual release. If you're going to publish your program, or I guess in our course, submit it as an assignment, I guess I would say, the suggestion is disable those tests, but don't actually remove the code from the release. And later on, I'll give you a suggestion about an easy way to do that. So that's kind of an interesting idea. I mean, it could be like a Boolean to do testing true or false, and then you use that to trigger the test cases. Or it might be like a global constant. Could be an idea. I've done that before to get into that test code, and then we'll see some other ideas about how to do that later on. Using stubs to test a class that's under development. We've said that before. If you're developing a class with a bunch of member functions, don't wait to start testing. Don't try to write the whole class and then start to test it and find out you have all kinds of problems and can't even make one of those objects. So the recommendation here is just write just write the smallest number of functions you can possibly get away with. Like you might need to do, I think they say this in chapter 1, you might need a constructor, you might need something to save some data, and you might need something to get some data out and confirm that it's actually storing it. So maybe you need 2 or 3 functions to get started. But immediately start writing tests for those. And if you need, and find out whether at least those basic functions are working before you add more stuff. Now, in order to get your test program to work, you probably need to provide some kind of function bodies to the other function prototypes in the class. And what we do is we call them stubs. Just make an empty function body. If it's a void function, just empty function body. If it's a value returning function, just return 0, right? And we make those stubs just so you can get the program to compile and start testing what you're working on. And then you go back and you add code to the stubs later on. That's a great technique. I do that all the time. And of course, once you have a complete class, you ought to have a test driver program, a specific test driver program that just makes one of those objects, calls all the functions in the object one at a time, prints out some kind of confirmation message that it's working as expected. Again, don't wait to make starting your test driver. You're working on the test driver bit by bit as you're making your class. And at the end, you ought to have this dedicated program that actually tests what we call the test driver, confirms that everything in your class is actually working according to spec, according to specification. Right? Same thing that we've had in our prior textbook, same thing that I've said, literally what I do when I'm developing programs. So I do agree with Mr. Carrano in this text. This is absolutely how you go about developing larger software programs. Okay, now here is a special tool that we have in the courses that I personally run called Style Scanner on these styling issues, as you're probably still learning about how to be a professional programmer here. So a program that I wrote that scans C++ code files and gives you some feedback about whether you're matching the standard styles. Of course, classes have capital letter names in their nouns, and functions have lowercase letter, camel case names, and all this kind of stuff. So the expectation in my courses is that you're going to check your assignments before submitting them with the program link below. So I have a link on screen here to where the program's hosted on GitHub currently. There ought to also be a link in the description to this video here. And what I ask my students to do is download this program, compile it, run it on the command line with the name of your code file as the argument. And you can see the example here. And it'll give you some feedback about things that you overlooked or things you forgot about that you need to fix before you turn your program over to somebody else to look for. For example, me as the instructor when I'm going to inspect it and grade it. Now, the program has a couple of switches for optional behavior. One of them that you're going to be using in this course is a -C switch. So when you run the program, you write style scanner space, name of your program .cpp or whatever, space -C. And what that does is it pays attention to there's a couple little differences with how Mr. Carrano styled his code in this particular textbook, and the -C switch will pay attention to that and permit those slight differences than how we did them in prior semesters. And we'll talk more about the differences in the follow-up video to this one, but I think that part of the learning issue here is 95% of these styling issues everybody agrees with, but different workplaces, different projects will have slightly different opinions about some of the details, and we know about that, we accept that. Different places will have a different style guide. The Google style guide is different from the Mozilla style guide, is different from the Apple style guide in little kind of small ways. And so we accept that, and when we move to a new project or to a new workplace, we will pay attention to those issues, and we will share, we will do as the Romans do, so to speak, and follow the same style as the project we're working in. So we'll be doing that, and again, it's 95% most of the same thing, but there are some differences, and if you use that -C switch, the style scanner program will understand that you're working in the Carrano style. Okay, so I think that of the appendices to the Carrano book, I think Appendix B is probably the most important one. And again, these are things that we could only talk about in our prior courses, and I'm glad that in our data structures course, we'll get to start to actually witness and experience the issues around maintaining existing code that already occurs. Reading it, understanding it, and then adding some features is really what a standard workday in a software engineering firm normally looks like. So we'll at least get a little bit more taste of that this semester. And I think that these issues that Appendix B highlights are among the most important things to kind of review to get started. Now, other things that you can review possibly on your own if there aren't videos for this is, again, there's Appendix A, which is a review of C++ fundamentals of data types and control structures and how to make a class and member functions and arrays and all this kind of stuff. And so if you are a little dusty, a little rusty, or just feel free to browse through that and remind yourself about what C++ looks like. The other thing is Appendix C is a review of the Unified Modeling Language, UML, that we have used previously to present class designs. And in this textbook, in this course, all of our class designs that we present will present in UML first. So make sure that you're familiar with what that looks like. Browse through Appendix C if you need to brush up on that. And again, as we present designs to you that we will later ask you to flesh out and build up, those designs will be in UML. So important things to think about. But this Appendix B is probably the highlight, and I'm glad, again, that we could touch base on, again, these bigger concepts that people who have worked in software engineering, it's kind of transparently obvious that, of course, you need to think about maintainability and readability and reducing scope and having functions be as small as you possibly can. That just becomes second nature to us. And probably as maybe sophomore level students, you're still learning about that, and we get to learn about that more this semester, so I think that's great. So next time, there'll be another video about one of the important appendices here. Like what's on my mind right now is what's called JavaDoc, documentation style in your comments. So I hope that you will join me again next time for that. I'll see you then.